Hey everyone, happy IMAC. I'm Julie, I work at VIBES.technology, and today I'm going to be telling you about how to get better test-based models and how you can do better FRF testing using our software DIRAC. So I only have a few slides for you today, just going into motivation and a little bit of introduction to our software, and then I'm going to switch over and do a live demo just so you can get a feel for how it works. And then at the end, I'm going to show you an application to an automotive component that we've done where we saw benefits using DIRAC and specifically using 6 degrees of freedom with the virtual point technology within DIRAC. I'm pretty sure most of the people watching this video have done FRF testing before, especially impact testing, and they know what a pain it can be to keep everything straight. So whether you're doing your tests for test-based modeling or modal testing or whatever it is, there's a lot of bookkeeping to be done with all of your accelerometers and impact points, where they are, what structure they're on, all of those sorts of things. So right now, I'd say the common process for most test engineers is you have someone take the data, and then there's usually a different person analyzing the data after the test is complete. So the test is complete, and then the test engineer sends over to the analyst the UFF files containing the data, a bunch of Excel spreadsheets telling you where the accelerometers and impacts are, if you're lucky. You'd probably get a long email chain with a bunch of details on how the test was completed. You'll either get a bunch of photographs of the test setup or maybe none. And then maybe you'll even get some hand drawings of where things were located or how things had to be moved and that kind of thing. So especially as we go to higher channel counts, we need higher accuracy. It just seems impossible to get good data using this process. You're bound to make a mistake somewhere, no matter how good you are. So if we use DIRAC instead for FRF testing, we're able to mitigate all the errors that you might run into with this process because we have a lot of data quality checks and just a lot of things within the software that help you get very accurate data. So the test engineer, he'll know right away while he's still at the test setup whether or not the data are high enough quality, and he'll even get some insights into the data, hopefully, while he's still at the test site. So what is DIRAC and what is test-based modeling? Well, DIRAC is basically just our software for doing FRF testing. So you can either use it for traditional modal analyses or to collect FRFs for, say, test-based modeling. So within DIRAC, it's not just the FRF testing. We facilitate the whole process from the measurement preparation, the FRF testing itself, and then some initial analyses and quality checks. So using this process, we're able to get much more accurate test-based models than not using DIRAC. But what is a test-based model? A test-based model is just a dynamic model of a component based on physical test data rather than, say, finite element modeling. These test-based models can be very useful for activities like dynamic substructuring or transfer path analysis. Usually we want to use test-based modeling in situations where the component is really complex and hard to model. So if it has complex damping, very complicated materials, difficult interfaces, things like that. However, we also might just want to use test-based modeling for a simpler component where we want to go to higher frequencies. Because I know some of you are really good at your finite element modeling, but when I tell you to go above 2 or 3 kilohertz, it's just going to be very difficult to get the accuracy you need for some of these activities. So that's where test-based modeling is really useful. One of the things people often struggle with test-based modeling is the difficulty of capturing rotations using traditional test equipment. Within DIRAC, we can set up regular accelerometers and use a regular impact hammer around a specific point and use that traditional FRF data set and the geometrical relationship of where everything is located to calculate the translations and rotations at a particular point of interest, which we call the virtual point. Using virtual points, we have the inputs and the responses at the exact same point. So using this type of FRF matrix, we can observe the true driving point nature and reciprocity that we would expect. But instead of me telling you about the theory behind virtual points, let's just open up the software and let me show you what we can do. First, let me show you the structure we're going to be testing today. It's the steering gear of a car, and I want to measure FRFs at the attachment points, so I can couple it to the rest of the vehicle using dynamic substructuring. You can see that I've already set up the accelerometers and marked some impact points around the structure. Now we're going to replicate this setup virtually in DIRAC. First, I'm going to drag and drop an STL file to load the geometry. In the 3D environment, I can easily navigate around the geometry and change the colors and other properties of the components. Now I'm going to add some accelerometers and impact points to the test. Here you can see the sensor database where I can add accelerometers, microphones, hammers, and custom sensors. Selecting the sensor I want, I can drag it around the geometry and attach it at the right place. Since it's glued to the STL file, the positions and directions are automatically determined. Similarly, for the excitation points, I can drag them around the geometry and place them where I'm going to be impacting. Now I can add a virtual point in order to get FRFs exactly at the interface. By selecting some sensors and pressing V, a virtual point is placed at their geometric center. If I now go to list mode, I can see the coordinates of all my sensors, excitations, virtual points, and geometries. I have the actual coordinates of that interface from my finite element model, so I'm going to paste them in here. Now let's make sure all the sensors and impacts are tied to that virtual point. And it looks like this interface is ready to go. Now let me just do the same thing on the other side and set up the rest of the measurement really quick. Now that the test is set up, we're going to begin measuring using Mueller's MK2 data acquisition system. If you don't have access to an MK2, you can still do your test separately and then import the results. However, as you'll see, the integrated testing in DIRAC is really one of its key features and really streamlines the whole process. Here we can connect to the MK2 using its IP address or a cloud station. Next, I need to define my input sources. In this test, I'm actually going to use two different hammers that excite different frequency ranges, and then crossfade the results. Here I also set my FFT parameters. Next, I need to map the sensors. Here you can see how DIRAC automatically recognizes my hardware setup, so I can drag the sensors and hammers directly to where I've connected them. On this page, I have some typical channel settings, and then lastly, I can set my windowing and try it out with an impact. Now I'm ready to begin testing. You can see how the excitation I'm working on is automatically highlighted. Let's do a few impacts. I can collect as many impacts as I want and then toggle individual ones on or off or delete them. I can also use the arrow keys to easily review all of the different responses. This allows me to review the response spectra as opposed to the input spectrum. Going to the next point, you can see again how the right excitation is automatically highlighted in the 3D viewer. Of course, the overloads are detected and automatically not included. Now I'll just finish up the rest of this measurement. Now that I've used two hammers, you can see in the input spectrum how they excite different frequency bands and are automatically crossfaded together within DIRAC. Now that we've taken some data, we're going to go to the Analyze module and take a quick look at how good our data quality is. Using the matrix viewer, we can quickly get an overview of a complete dataset. Here I'm using it to review the average coherence up to 2000 Hz, but as you can see, there are also some other options. My coherence is really good, but I can zoom in to see which impacts are the worst. I can easily toggle specific impacts on and off to get the best coherence possible. Another useful feature is the animation of the operational deflection shape. I'm going to review the ODS at the low frequencies to ensure my test setup is correct. Hang on, one of these sensors looks a little funny. It's not moving with the other ones how I'd expect. Let's check out the response consistency of the sensors. Oh yeah, it definitely looks like one of these channels has an error. Let's go fix it in the Prepare module. Sure enough, looking at my test setup, I can see that I put one of the sensors in the wrong orientation. Let me just fix that angle. Go back to the Analyze module and refresh the consistency matrix. Now doesn't that look better? Now let me show you how the ODS can give immediate insights into the dynamics of our structure at the higher frequencies. Yep, that's definitely a bending mode. Lastly, let's switch to virtual point mode. In this mode, I can review the response and force consistencies on an average overall sense. These diagonal terms are now true driving points and also capture rotations. Reviewing the off-diagonal terms, I can see how good my reciprocity is between different points. Looks pretty good to me. Now that I have a good data set, I can export it to a UFF, an ATFX file, or directly to MATLAB. Hopefully now you see how easy it is to get accurate FRF data using DIRAC. Now I'm just going to show you a short example from a project we did recently on an automotive component, the electronic roll control, or ERC. Now in this project, we wanted to determine the forces that the ERC exerts on the body using component-based transfer path analysis. So basically to do this, we install the ERC in the vehicle, we measure some operational responses while the ERC is operating, and then we also measure some FRFs while everything is static to get the relationship between acceleration and force, such that we can calculate the forces that the ERC exerts on the body. Now you can see in this diagram that the interface between the ERC and the vehicle, there's an actual interface there. So I can't actually impact exactly where the interface is because it's installed. So we're going to be doing this TPA using 3 different techniques. In the first case, we're just going to do the impacts next to the interface, and we're only going to use 3 degrees of freedom to approximate the forces. So no rotations are being included here. We're not doing anything to the FRFs. We're just using the FRFs themselves to calculate the forces. In the second case, we're going to use 3 degrees of freedom again, but this time we're going to use the virtual point transformation. So we're going to do a few extra impacts around the interface and then use the virtual point transformation basically to average out some of the error. And then in the third case, we're going to use the virtual point transformation with 6 degrees of freedom. So we're going to capture both forces and moments that the ERC inputs into the vehicle. Now, the way we're going to compare our results, we're going to take those forces that we calculate and apply them back to the vehicle and predict what the response is at a location of interest, in this case on the seat rail. You can see using the first approach with just 3 degrees of freedom and no virtual point transformation, I get the worst results overall. There's kind of just some noisy spots all throughout the bandwidth, and overall it just doesn't look great. However, then if I go to the 3 degree of freedom case where I'm using virtual point transformation, you can see that the results are generally improved a little bit from the first case. So I have less noise. However, some of the results at the higher frequencies aren't as good as I'd like them to be. This is where if we go to the 6 degree of freedom case, we see we get the best results across the entire bandwidth. So this kind of shows the importance of including rotations, especially as we go to those higher frequencies. This was just a very simple case, but we've seen it in a lot of projects that including rotations and just using the virtual point in general really improves our results for things like TPA or substructuring, especially when we're combining either test-based models, finite element models, or any combination of those. So that's all I have for you today. I hope you enjoyed my talk, and if you have any questions about what I presented or our software or anything, you can get in touch by sending me an email. Thanks!